Let us start lecture 30 and the topic is phase diagrams in single component and binary systems. For the last few lectures we have been talking about condensed solution and our interest is to finally calculate free energy of mixing or the Gibbs free energy of mixing. Now, we have treated ideal gas mixture and then while starting a discussion on condensed solution, we have actually taken everything into the gas phase. How did we do that? We have taken the equilibrium vapor pressure of any component in a solution and how those equilibrium vapor pressure relates to the vapor pressure of those components in the pure condition, and from there we have found that how we can actually, so that equilibrium you can, if we can consider in the gas phase which is in equilibrium with the condensed solution, we can definitely get the information about how the solution is formed. Okay. So, our interest would be that only, and we have seen two laws, Raoult's law and as well as Henry's law. Our treatment on the solution in the beginning would be based on Raoult's law. So, that means we will talk about ideal solution. So, today's topic would be again the condensed solution, measurement of Gibbs free energy of mixing, and we will take Raoultian solution behavior, or we will take ideal solution. Okay. And when we talk about ideal solution, when we deal with the vapor pressure or the equilibrium vapor pressure of any component in the gas phase, and gas phase would also have mixture of all the components in the gas phase. So, that time that gas phase will also be considered as ideal. So, actually you are treating idea of this condensed solution on the basis of ideal vapor phase mixture in equilibrium with the condensed solution, fine. So, when we talk about ideal solution, we take Raoultian solution behavior. So, we will be taking this concept Pi equal to Xi Pi naught, and we are talking about one particular temperature, temperature is fixed, fine. So, Pi is the I is the ith component in the solution. So, and Pi naught can be, this is the saturated vapor pressure when I is in the pure condition. So, that can be considered as a reference state. So, now we have understood standard state as a reference state. So, this saturated vapor pressure at a particular temperature for pure case can also be taken as a standard state. So, that means it is basically a reference point. With respect to that, we are measuring all the other pressures. So, this is another important aspect. Now, when we talk about solution, whether it is a mixture of gases or solution, there are two ways to define concentration. One way is definitely is a most easy way of defining concentration. Defining concentration, that is basically mole fraction or Xi. The most easy way one can do that. The other way is basically bringing in activity. We call it activity of ith component in the solution, or we can say active concentration. And this activity Ai can be related to one quantity called is fugacity. So, instead of pressure, so this is Fi naught and Xi is nothing but Pi divided by Pi naught, fine. Now, what is the difference? So, this F is basically called fugacity, and this is actually having a similar behavior with reference to pressure. similar behavior with reference to pressure, fine. So, when we talk about, for example, when we started discussing about chemical potential, we started about escaping tendency, is that correct? So, we talked about escaping tendency. So, while talking about escaping tendency, we said that if T1 greater than T2, heat will escape from T1 to T2. When we talked about P1 greater than P2, the pressure, molecule from high pressure to P2, okay. Or we can also say that molecule will try to expand, you can also say that expand, fine, expand in order to reduce the pressure, if there is a chance of reducing pressure, fine. So, that means you can also relate this fugacity as escaping tendency of molecule. In fact, there is one more, let us say chemical potential of I in phase 1 is greater than chemical potential of I in phase 2. So, that also reflects escaping tendency of molecules or atoms from high mu I to low mu I. Okay. So, and that time of course, P and T are constant. So, this is fugacity is also related to escaping tendency of molecule, fine, and it is basically having a similar nature with reference to pressure, but it is not equal to pressure, remember, equal to pressure only if we consider ideal case. Now, here Fi is basically fugacity of ith component in solution, and Fi naught is basically fugacity of ith component in pure state, fine, or pure condition, and this can be considered as a standard state, fine. This can be considered standard state, and remember every time this is specific to that particular temperature what we are considering. And here the solution has a specific nature. What is that nature? It is basically called real solution, real solution. So, that time fugacity can be taken instead of pressure. But if we consider ideal solution, that time Fi can be taken as Pi and Fi naught can be taken as Pi naught. So, activity of I becomes Pi by Pi naught. So, it is actually becoming Xi. Okay. So, in case of ideal solution, Ai equal to Xi, activity is equal to mole fraction. So, now let us go to a treatment of condensed solution. Now, we are not specifying whether we are considering liquid or solid. Now, in case of liquid, we will be treating with respect to evaporation rate. In case of solid, we will be treating with respect to sublimation rate or deposition rate, okay, in case of solid. So, now when we talk about this, let us have a situation like pressure and temperature. Let us take a situation where with respect to ith component, see if I try to look at, and we are trying to find out Gibbs free energy for formation of solution. So, let us say we are taking T to be constant. So, that means at a particular temperature we are treating it. Okay. Now, if I take a situation like a 3-step process, let us consider one process of converting of ith component from pure I to I with a of pure I with I in solution. Okay. So, actually if we consider pure I, that time the pressure would be P I naught, vapor pressure, saturated vapor pressure. If we talk about I in solution, that time it would be P I, fine. And we have a system like this, okay. And now we have a solution. So, now this is at a particular temperature T and it is a closed system, let us say. Okay. Now, the stage 1, let us say, stage 1 is converting 1 mole of condensed I, pure I, to its vapor under equilibrium at temperature equal to T. So, what will be my vapor pressure? P I equal to P I naught. Now, the second stage, I will convert one mole of pure I vapor to from P I naught to P I. Okay. And this P I is basically, had it been a solution of A in B or I in a solution. So, that means if I is a component in a condensed solution, in a solution. Okay. So, that time that partial pressure, the equilibrium vapor pressure should have been P I. We have already understood that. And the third stage is basically convert 1 mole of vapor of ith component to condensed solution, fine. These are the 3 stages we are considering. So, that means here P I, this is particular pressure, that means P I should have been my equilibrium vapor pressure when it is in solution. So, now if you see, so this is also under equilibrium. Why? Because since it is under equilibrium, that is what P I becomes equilibrium vapor pressure of ith component in the solution. Fine. So, now you see out of 3 stages, which stages are in equilibrium. So, this stage 1 is in equilibrium and stage 2 is under equilibrium. Okay. Now, every stage there could be a free energy change. Let us say the free energy change corresponding to stage 1 is delta G 1, delta G 2 for second stage and delta G 3, and since this third and first and third stages are happening under equilibrium, so they should be 0. So, that means the total free energy change should be equal to delta G 1 plus delta G 2 plus delta G 3. So, this goes to 0, this is 0. So, finally, it leads to, it is basically delta G 2, and delta G 2 is nothing but, we have seen, is nothing but G I, we can say that partial molar Gibbs free energy in solution minus G I molar Gibbs free energy in pure I condition, in pure I of ith component in solution. So, this pure I. So, that is nothing but RT ln Pi divided by Pi naught. Okay. So, and since we know activity of I equal to, if I try to write in terms of activity Pi divided by Pi naught, so I can write it as RT ln activity of I. This can also be written as G I bar minus G I naught. Why? Because this G I naught can be taken as standard state. Since we are talking about saturated vapor pressure under pure condition at a particular temperature T, we take it as a reference state. So, that becomes it a standard state, and this is for the pure condition. So, this should be equal to RT ln AI, and we have taken 1 mole. So, that is what this becomes true. So, once we have this particular relation, so then this difference delta G, and with respect to I, remember this is with respect to ith component. So, this quantity can become since it is basically a partial quantity. So, we are talking about only the free energy change due to the solution formation of ith component. Okay. So, we can write this one as delta G bar, and this is with reference to I, this is for the mixing. So, M is basically mixing. Okay. So, that becomes, and this is the ith component, that becomes RT ln AI. Fine. Now, if I try to treat, so we got a equation like this. For example, if we take binary solution and we have say A B, that time we can write delta G A M, which is basically this delta G M bar I can be written as partial molar Gibbs free energy difference for the formation of ith component in a solution. Fine. This should be then RT ln AA and then delta G Bm equal to RT ln AB. So, we get for the dilute solution like that, and this is at a particular temperature T. Now, so this is T constant, remember all those cases T is fixed. So, we are doing it at a particular temperature. So, once we have this, so then we can actually find out what would be the mixing free energy change. So, now if I try to write G total before mixing and G total, so G total and G total before mixing, and if we talk about the standard condition, so this will be like this and this would be bar G total after mixing, or we can say just mark it like this prime and G double prime after mixing, and let us say we are talking about AB binary solution, fine, and let us say number of moles to start with is Na number of moles and this is Nb number of moles. So, this is number of moles of A and B. Okay. And now, since we have expressed everything in terms of partial pressure, so we can actually take T as well as P constant. Fine. We have taken, because we have taken not partial pressure, we have taken everything in terms of activity. So, active concentration of those elements in the solution. So, that can be considered as P and T can be considered as constant. So, that case G double prime minus G prime total and total should be equal to Na Ga bar plus Nb Gb bar, which is nothing but G double prime total minus Na Ga naught minus Nb Gb naught. This is G total when they are in pure condition. Okay. So, this is pure, this is after mixing. So, then I can write, so this is nothing but delta Gmix equal to, and which is delta Gmix is gives free energy of mixing for solution, or we can say gives free energy for the formation of solution. Okay. So, then Na Ga bar minus we can write this. So, this becomes Na delta G M A plus Nb delta G M B. So, this is actually for total. Okay. And if we want to find out, or let us say since I am talking total, so this is physically total gives free energy of mixing of for solution and or gives free energy for the formation of solution. So, then if we want to find out for 1 mole solution formation, so then we can write is Na plus Nb. So, that the total number of moles that are there in the solution would be equal to Na divided by Na plus Nb delta G bar M A plus Nb So, this becomes now delta G mix, which is basically gives free energy, or we can say for the formation of 1 mole solution, or simply gives free energy for 1 mole mixture, 1 mole this is, or we can say gives mixture or gives free energy of mixing okay. So, would be equal to, this becomes XA delta G M plus XP, that is, there should be a bar B M. So, this equation we are getting, and this can actually get to delta G mix equal to XA RT ln AA plus XB RT AB. Now, if we take dilute solution, obeying Raoultian behavior, all those components are behaving in Raoultian solution law. So, then we can write AA equal to XA as well as AB equal to XB. So, then this particular equation, this equation would go into, would become in fact, this is a very critical equation, and we will be dealing with this equation when we start drawing phase diagrams, actually start drawing change in free energy when it is mixed, when the solution is formed, as well as we are trying to calculate, let us say we want to see the behavior of mixing entropy, or we want to see the behavior of mixing enthalpy. Every time these equation will be referred, this particular equation where del G mix equal to XA RTL and XA plus XB RTL and XB in case of binary. Okay. So, let me stop here. We will start dealing with this particular equation from next class onwards, and you will see gradually we will get into a situation or the equation which will help us to draw phase diagram. So, let me stop here. Thank you very much.